Alright, we want to look at this very question. The question says explain the following terms. We have free electrons, we have holes. Now, we want to explain these terms, but we must know that these terms come from and are used in electronics, and particularly for semiconductors. Now, we want to look at what a semiconductor is, because if you must be able to understand what we mean by free electrons and holes, we must know what a semiconductor is. A semiconductor is a material whose conductivity is between the conductivity of an insulator and that of a conductor. What this means is that the conductivity of a semiconductor is less than what that of a conductor, and it is greater than that of an insulator. So that is just basically what we want to look at. We have some examples of semiconductors. Some examples, and a very good example is silicon, and then we have germanium and the rest. Now, I would like us to know some facts about semiconductors. You must know that a semiconductor behaves like an insulator at very low temperature, and in fact, the conductivities of semiconductors increase with increasing temperature. At very high temperature, even insulators behave like semiconductors, and at low temperature, all semiconductors behave like insulators. And this is why you see that bodies that are very high temperature, they can conduct electricity. For us to understand why it is so, now I want to look at what really a semiconductor is. How do we view it? Now look at the image we have here. This is how a semiconductor is viewed. Now, a semiconductor is a material that contains two bands. These two bands are called the valence band and the conduction band. Now, it is believed that at 0 Kelvin or absolute zero temperature, the valence band is completely filled with electrons that is required to be there, while the conduction band is empty. Now, when temperature increases, that is, for instance, when the temperature is at room temperature, now some electrons in the valence band, they gain energy, and they can which they now move to the conduction band. And now when they leave the conduction band, they leave some space, which these space are called holes. And as we know already that electrons should be negatively charged. Now the holes are not supposed to be positively charged, but because of what left there is electrons. So now since electron has been removed, so they now behave as as positive charge. Now, and if a PD or a voltage is connected across this very semiconductor, it will conduct electricity, because of the valence band and the conduction band have different amount of electrons. So these electrons will be moving away from the valence band towards the conduction band, and you know that the movement of electrons constitutes what we call current. So that is how the whole system will conduct electricity. If this was a pure sample of, say, silicon, now you must know that when you have a pure sample of a particular semiconductor, it is called an intrinsic semiconductor. We will talk about that now, but let's talk about two important things here. I want to talk about free electrons and holes. What are they really? Now, as can be seen from that very image that I showed to you, free electrons are negative charge carriers in a semiconductor. So they are the ones that are free to travel from the valence band to the conduction band, and holes are simply the carriers of the positive charge. Though I told you that they are not really positive because of electrons left there that very hole. So the hole behave as what? As a positive charge. So that's it. Now, like I said before, if we have a pure sample of a semiconductor, we call it an intrinsic semiconductor. But when impurities are introduced into a semiconductor, such semiconductor is called an extrinsic semiconductor. Now, an extrinsic semiconductor is a semiconductor that impurities are introduced into it to increase the conductivity of such semiconductor. Now, the process by which these uh, impurities are introduced into the semiconductor is called doping. So that's it. I believe this video has helped you. Please do subscribe to the channel. And this question says, state the principle of operation of fiber optics and also state two applications of fiber optics in medicine. Now, for us to be able to answer this question, we have to look at what an optical fiber is. So it is just a glass made of a thin wall of glass which has a tiny hole in it through which light travels through without leaking away. Not just light, other signals such as other electromagnetic waves can travel through it without leaking away. And so this very uh, optical fiber depends on some uh, property, physical property for its operation. Now, the main property that it depends on is total internal reflection. The inner core of the optical fiber has a diameter which is about 6 between 6 and 250 micrometer. Now, this very inner core has a very small refractive index, and this is what allows for the total internal reflection. Fiber optics has so many applications. It ranges from uh, telecommunication to medicine to the very light, all those Christmas trees and stuff like that that you have in your house. Now, the next question says, define diffusion and also state the factors that can affect diffusion. Now, diffusion is the movement of particles of a particular substance from a region of high concentration to a region of low concentration. And some of the factors that can affect diffusion is the surface area of the material, the mass of the material, the density of the material, and so many other things like that. Now, this question says, state Newton's law of universal gravitation. Now, Newton's law of universal gravitation exists between bodies which are under gravity, and it simply states that if two masses are separated by a distance d and they possess mass m1 and m2, the force between the two masses is proportional to the product of their masses and inversely proportional to the distance, the square of the distance between them. And so this is one of the inverse square laws, and this also applies. Another example of inverse square law is uh, Coulomb's law of electrostatics. So this very law tells us that what two bodies who are separated by a distance possess attract themselves with some force. Now that force is proportional to the product of their masses, but inversely proportional to the square of the distance between them. And this is the formula that represents it. Now, in this very formula, we see a capital letter G there. This capital letter G represents the the proportionality constant, and it is called a universal gravitational constant. it is the same everywhere in the universe. Now we must know that this very gravitational force can exist between objects which are as small as electrons and protons, and it can also exist between objects which are as large as a planet and the sun. So, and it can also exist between a planet and satellites that are revolving around it, such as the natural one which we call the moon, or the artificial satellites which are used for telecommunication and other purposes. Now, the next question says define gravitational field. Now, before we can understand what gravitational field is, let us look at what is a field. In physics, what is a field? Now, a field is a region of space within which the effect of some physical agency can be felt. Now, talking about gravitational field is a region of space in which the effect of gravity can be felt. Don't forget that we have other kinds of field, such as electric field, magnetic field, field due to heat, which are going to be scalar field, and other kinds of field like that. Now let's go to another question. This question says derive the equation relating the universal gravitational constants G and the acceleration due to gravity. Now I would like you also to now for us to be able to answer this very question, we must know that anytime we are asked to find the relation or relationship between two quantities in physics, all we are simply asked for is a formula that relates them, a formula that you can use to either you can express one in terms of the other. That is just what we are asked. Now, for us to be able to answer this very question, all we need to do is we need to know Newton's law of universal gravitation, which I have explained to you earlier in this video. And I will say that what the force of attraction between two bodies which are separated by a distance is equal to what? The product of their masses divided by what? By the square of the distance between them. And having looked at that, if now we want to look at the force of attraction between the earth and a body of mass m. Now when we put m1 to be what? The mass of such body to be m, and we put the mass of the that is m2, make m2 to be the mass of the earth. I call it what? M subscript e. And if I put that, then I have a new equation, which is what? F equals what? G m me, that is mass of the earth over the radius of the earth. Now why do we use the radius of the earth? We use the radius of the earth because the for us to be able to work out this kind of equation, or to derive this kind of equation, we are going to take it that the mass of the earth, that's one of the conditions for which this very law holds. We are going to take it that the mass of the earth is concentrated at the center of the earth. So that radius there is what? The distance between an object which is on the surface of the earth and the center of the earth, and that radius of the earth
is about 6,400 kilometers approximately.
Let us work with that. So, and we remember that was even before we talked about Newton's law of universal gravitation, there is this force that we know, which is what? The weight of a body. The weight of a body is what pulls a body downward if it is thrown upward. That very weight is the force of what? Gravity on such body. And this same force of gravity will be equal to the force of that is the force that is represented by the universal law. Since the universal gravitational force equals the weight of the body, we can equate the two equations and find the relationship between the universal gravitational constant and the acceleration due to gravity. Now, we can see that that the mass of the object is common to both sides of the equation, and so we can cancel it out, and when we do that, we are able to get the relationship between the acceleration due to gravity and the universal gravitational constant, with the acceleration due to gravity as the subject of the formula. You can also make the universal gravitational constant the subject of the formula, but that is not necessary. This equation that we have derived is sufficient to answer that question. Now, the next question says, state two assumptions on which the relations hold. That is, G equals G ME over R square. Now, I would like to. Now, under what condition does the equation that we have derived hold? I have talked about it, at least one of them, during the explanation in the previous clip. But then I would like you to think. Can you pause the video and try to remember? Alright. The first condition is that the mass of the earth is considered to be concentrated at the center of the earth. And the second condition is that the earth is assumed to possess uniform density. And the third is that the earth is spherical. So those are the conditions necessary for the equation to hold.
The next question says, that's number 8C. Say calculate the force of attraction of between a star of mass 2.0 times 10 raised power 30 kg. We have 2 times 10 raised power 30 kg is the what? Is the mass of that very star, right? And the earth, assuming that the star is located 1.5 times 10 raised power 8 kilometer from the earth. So the star is what? The radius, that is the distance between the star and the earth, is what? 1.5 times 10 raised power what? 8 kilometer, right? Now, and then we are told to take the mass of the earth to be what? 5.98 times 10 raised power 24 kg. So the mass of the earth is what? 5.98 times 10 raised power what? 24 kg. And also, we are also told that, as we know the G, which is what is which is a constant. G equals 6.67 times 10 raised power what? Minus 11 Newton. No, the unit there is we have Newton meter square per what? Per kg square. Now these are the things we need to solve that very problem. We know that what? F equals what? G m1 m2 over what? R square. So now let us look at these things. Do they really, all of them, all these quantities, are they in the SI units? Everything is in the SI units apart from what? The radius. So this radius is what? In kilometer. Convert it to meter. We are going to have what? 1.5 times 10 raised power 8 times what? Times 1000, right? Then meters. Then this 1000 I can erase it and add 3 to this power. So this is going to be what? 10 raised by 11. So that's just what it is. Then let's solve this now. What is F going to be? Now F is going to be, G is what? 6.67 times 10 raised by what? Minus 11 times the mass of the sun. Let us take it to be M1 is what? 2 times 10 raised by 30 times the mass of the earth, which is what? 5.98 times 10 raised by 24 over r square. We have 1.5 times 10 raised by what? 11, everything squared. Let us punch this. So I have 6.67 exponential minus 11 times 2 times 10 exponential 30 times 5.98 times 10 exponential 24 divided by 1.5 exponential 11 squared. So this is what we have. We have 3.5. We have it at what? F equals 3.5 of 3.55 times 10 raised by what? 22 Newton. So that's the force between the star and the earth.
Now, what is escape velocity? Now, escape velocity is the velocity that is needed by a body which is revolving around a planet in an orbit to escape the gravitational influence of such planet. Now, if a body is revolving around a planet, that's going to be a satellite, like the artificial satellites which are used for telecommunication and some other purposes. Now, that minimum velocity that is needed for that very object to overcome the gravitational influence of the earth is what we call escape velocity. Now, this next question says differentiate between acceleration due to gravity g and the universal gravitational constant. Now, capital letter G is used to represent the universal gravitational constant, while small letter g is usually used for acceleration due to gravity. Now, what are these two terms? Now, acceleration due to gravity is the force on a unit mass in a particular place or region. So that is what it is. But g is just a constant, that is, as the universal gravitational constant is a constant which is the same everywhere in the universe. Now, the small letter g, acceleration due to gravity, depends on where you are. So it is not a constant everywhere in the universe. So it varies from place to place. But capital letter G there is what? Is the same on the moon, on earth, and any other place in the universe. But small letter g is lesser in the moon than in the on earth here. So that's just one difference. Another difference is that this capital letter G, universal gravitational constant, is measured in Newton meter per kilogram square. That is the SI unit. Whereas the acceleration due to gravity is measured in meter per second square or Newton per kilogram. That's Newton per kilogram. That's another difference. Now, another difference between these two is that the universal gravitational constant is a scalar quantity. So it does not have it has only magnitude but no direction. And but Acceleration due to gravity is a vector quantity. For instance, if you are lifting a load on Earth, you are going to be doing work against gravity, that is, against the gravitational pull of the Earth. So, and if the load is going to fall, it's going to fall against, towards the direction of gravity. Now, I believe that you have really learned from these videos that we have been posting on physics past questions. If there is any topic challenging you in physics, chemistry, or mathematics, do well to comment. And also, please don't forget to subscribe and turn on that notification bells, and also like the video because it gives us the encouragement to continue.